Now, let's take a moment and look at some important characteristics of the particular solution, because that's going to tell us some very important um, aspects of the force vibration response. So instead of going and solving for A and phi like we did, since this is a review, I'll leave that to you to look at in one of a number of textbooks. But let's take a few minutes and look at the particular solution, because that's going to tell us some very interesting results associated with the force response of an undamped oscillator. So if we take the particular solution for a moment and just look at that, we can rewrite it as shown on this chart. Xp of t is equal to f over omega n squared m divided by 1 minus omega squared over omega n squared times cosine omega t. So all I did in rewriting this expression was to take omega n squared out of the denominator, write it in the numerator, and then write the denominator as 1 minus the ratio of the square of the driving frequency to the natural frequency. Now if we apply the definition of the natural frequency, remember omega n squared is equal to k over m, then the term in the numerator simplifies to f over k. The denominator stays the same. And so again, another version of the particular solution is xp of t is equal to f over k over 1 minus the ratio of the squares times cosine omega t. Now why do we do this? Well, what we can do is we can take this expression and try to understand what's going to happen in different regimes as omega changes relative to omega n. So if we look at that expression, we can start drawing out some important features which give us a better understanding of the force response of an undamped oscillator. Let's first look at the term f over k. Term f over k is equal to the static displacement if you would apply a constant force of amplitude f to a spring with stiffness k. And so you can think of the term f over k as sort of a quasi-static term. If you took a constant force of amplitude f and applied it to a spring k, the static displacement would be the ratio of the applied force to the spring stiffness. And again, if you look at the units of that, f over k, you'll find that the units are in displacement, which makes sense. The other important feature of the response is that the amplitude of the force response is a function of the ratio of the excitation frequency omega to the natural frequency. So what we would expect is the amplitude is going to change as the excitation frequency changes relative to the natural frequency omega sub n. So if we look at this in more detail, we'll note that there's really three regimes that are of importance. The first regime is when the excitation frequency is much lower than the natural frequency. So if omega is much less than omega sub n, then we note that the ratio of omega over omega sub n is much less than 1. Now in this case, the particular solution can be approximated simply as f over k times cosine omega t, and that's because the denominator 1 minus omega squared over omega n squared is approximately equal to 1. So what this tells us about sort of the type of response is that when the excitation frequency is much lower than the natural frequency, then the amplitude of the particular solution is equal to, or essentially equal to, approximately equal to, the quasi-static amplitude f over k. And so at frequencies, driving frequencies much lower than the natural frequency, the amplitude of the force response is going to be approximately equal to the quasi-static amplitude f over k. Now the second regime of interest is the opposite end of the spectrum. Let's assume for a moment that the driving frequency is much greater than the natural frequency. In this case, omega over omega sub n is much greater than 1. So if we take the particular solution and assume that omega over omega sub n is much greater than 1, then what we get is the particular solution can be approximated as xp of t is equal to minus f over k over the ratio of omega squared to omega n squared times cosine omega t. In this case, we note a couple important features of the amplitude. First, we note that the amplitude is 180 degrees out of phase. That's the minus sign that's in front of the amplitude. So frequencies, driving frequencies much larger than the natural frequency of the system, then the force response is out of phase with the input. Also important is that as omega over omega sub n becomes larger, the amplitude of the particular solution decreases as the square of the excitation frequency. And so what we can see is that as the driving frequency gets much, much larger than the natural frequency, the amplitude of the force response is going to be attenuated, or it's going to be decreased as omega gets larger. Now, the final regime of interest is, in many ways, one of the reasons why vibrations is an interesting topic to study, and that is because when the driving frequency is near the natural frequency, we get a significant amplification of the force response, and we can see this in the expression for the particular solution. So let's go back to our expression for the particular solution and assume that the excitation frequency omega is approximately equal to the natural frequency omega sub n. Now in this regime, the amplitude of the particular solution, which represents the amplitude of the force response, will be significantly larger than the response in the other regimes. And this is because the denominator of the force response is getting close to zero. Now, of course, this phenomena is the phenomena of resonance, and that is resonance is defined as when the driving frequency is equal to the natural frequency. And near that, if the driving frequency is close to the natural frequency, then the solution to the differential equation shows us that the response, the force response of the system, will be amplified significantly, which tells us that exciting an oscillator near resonance results in a significant increase in the force response. Now, resonance is defined as when the driving frequency omega is equal to the natural frequency omega sub n. The solution methodology that we've used so far to calculate the force response, or the particular solution, actually does not work when omega is equal to omega sub n. In this case, because the particular solution has the same form as the homogeneous solution, you need to use a different form of particular solution to calculate the solution to the differential equation. We aren't going to go through this in detail, but if you do this, you'll see that what happens is that when omega is equal to omega sub n, the solution contains an oscillatory component, cosine omega nt, but it also is unbounded because the particular solution has the variable t in the amplitude of the particular solution. And so the form of the particular solution when omega is equal to omega sub n is provided below, and you can see that as time gets larger, the solution becomes unbounded, which is what you'd expect given the fact that the oscillator is undamped and the excitation frequency is exactly equal to the natural frequency. Now we can visualize these different regimes of the solution by plotting the amplitude x, capital X, as a function of the frequency ratio omega over omega sub n. You can see from the plot on this chart that when omega over omega sub n is much less than 1, say less than 0.1, this is the quasi-static regime that we talked about earlier. In this regime, the amplitude of the forced response is approximately equal to F over K. What we've done on this chart is normalize the vertical axis to be equal to 1 when the solution is F over K. Now, in the other regime, the second regime that we discussed, you can see that In this case, when omega over omega sub n is much larger than 1, the amplitude of the force response is attenuated. The difference between the blue and the red curves denotes the fact that at low values of omega over omega sub n, the two responses are in phase. At large values of omega over omega sub n, values greater than 1, the response is attenuated and it is out of phase. Now there's a regime in the middle when omega is approximately equal to omega sub n, or in this case, in this chart, omega over omega sub n is approximately equal to 1, where the response is amplified. And of course, as the driving frequency becomes close to the natural frequency, as we just discussed, the response becomes unbounded.